So let me just clean up some loose ends. What I'm going to do now is try and take the Hankel transform of at least the spatial profile of the pump and probe beam. So both of those laser beams are Gaussian beams, meaning that the intensity profile on the surface follows a Gaussian that goes outward from the central radial. If you normalize them in the correct way, then they show up as I've shown them here, where the total absorbed laser power appears as a prefactor that I'm calling A out in front of the pump spatial profile. And inside the actual Gaussian, there's a denominator term that characterizes how wide the laser beam is, and that's called the 1 over e squared beam radius. The probe profile looks exactly the same. It's also a Gaussian, and the only real difference is that the way that, at least that I've been doing the math, I've been normalizing the intensity of the probe beam such that when you integrate it over the entire profile, you get a total power of 1, so that we can use it as a probability distribution. So then all we need to do is take the Hankel transform of those two things. But it turns out that a Gaussian, when you take the Hankel transform, remains a Gaussian. And in fact, the normalization terms that are out in front just go away. And so for the Hankel transform of the pump beam, it just has the prefactor A, which is the power, times another Gaussian with the same size and shape, and similarly for the probe beam. And so that's really all there is to it. And although Cahill doesn't do this as an original paper, but you might think about the fact that the pump and probe might actually have a different spot size in a real TDTR system. So I'll just leave them that way.